I'll introduce you slowly. So William Grisaitis is a machine learning engineer and curious person in Orlando. He grew up in Orlando, graduated from Duke. He did some work at the Howard Hughes Medical Institute, contributed to peer-reviewed research in deep learning and computational neuroscience. He's currently a freelance data science consultant in the Orlando area. Previously worked at Capital One's in credit cards and small business lending, and he's going to talk to us about deep learning on mobile devices. So, William.
Thank you so much, Aaron, and thank you so much to everyone here for making it out tonight. I'm really excited to be joining all of you to discuss deep learning algorithms that can run on smartphones and other hardware that is not as computationally rich as a GPU, which we've probably heard a lot about in the context of the success of deep learning over the past couple of years. I don't want to go super detailed right this second, but there have been a lot of really fascinating and amazing advances in the abilities of relatively simple computational hardware to do especially image processing tasks, and basically anything else that deep learning has been applied to. But I'm mainly going to be focused on image recognition and a little bit of object detection, because that is especially relevant for smartphones where you have a camera, and we're more intuitively familiar with probably how certain applications of the technology there could work out. So to start off, I have my clicker here. I feel so powerful. Some acknowledgements, a little more. Thank you, of course, and also to Tio and Aaron for putting this together, and the analytics meetup here, the group here at UMiami, and the various organizations of meetup groups. It sounds like there's like a new PyData Miami organization that is kind of starting, which is great. Also, I mentioned Srinivas Turaga. Srini was my first academic advisor. Actually, not my first, technically. I did some research in college as well, but as Aaron was describing, a couple of years ago, I worked in a research lab as a research assistant and software engineer in a deep learning research lab, and it was Srini who brought me on as kind of his main computational guru. He was working in deep learning before it was called that, and actually left the field because there were no jobs in deep learning for him to do. So he did postdocs in other fields and then came back to deep learning later. He's a really amazing guy. Also my family and friends, of course, and can't go without thanking Wikipedia and Archive as well. I mean, I've probably learned more from Wikipedia than maybe human experience itself. And yeah, you guys, so thank you again. So why should this talk interest you? I know you're already here, so we have kind of a selection effect where all the people who aren't interested aren't here. I wish I could talk to them as well. Yeah, there are, as I was alluding to earlier, there have been a number of developments in not just deep learning as an overall field in terms of, I'm not even going to go over the whole area because I couldn't even do that anyway. But specifically for running on things as slow as your phone, there have been a lot of improvements in algorithms, which I'll be going over. That'll be most of the focus of my talk. Unfortunately, I'm actually not going to be sharing any code. This is all mainly going to be how things work, certain advances that have happened that enable smaller network architectures that can achieve levels of performance that used to be the state of the art on GPUs. But also there have been some phones have gotten faster, batteries have gotten better. What else? I have actually a few things here. Cameras on phones are getting better. Now they're going to be, it's more common now for phones to have multiple cameras, which then enables new types of depth perception in images. in a way that enables perhaps new applications of using a smartphone, using AI. And also with, as far as like new possibilities and spillovers, well, with the possibilities, yeah, now we're not really enslaved to just using GPUs anymore. We can use these algorithms in our pocket. And in terms of spillover with other industries and so on, I was thinking, this is one area that I kind of want to touch on toward the end of the talk, but I think it's very important because it's really about application and why this is relevant, not just academically, though that's interesting as well, but in terms of how this can make the world a better place. So things about things like robotics, Internet of Things, any sort of hardware that has sensing involved, like a Nest in your home, like those little smart sensors. Really, any device that is marketed as smart today, I mean, with this type of stuff that could run on a simple, what is it called, like an integrated circuit on that device could be much smarter, like what we are calling a smart fridge today. If a fridge could use object detection internally to know exactly what groceries you have and how old they are and forecast when they're going to go bad. I mean, that's something that fridges aren't doing today, but it probably could. And that's it's a market opportunity that, I don't know, some of you may want to start a business in this and develop some of these products. At least I do. This is one reason why I'm actually working in this area right now. Full disclosure, I'm interested in starting a business using this technology, which is why I'm obsessed with it recently. So, and a couple other ideas. Oh yeah, self-driving cars. This is probably the #1 area that has application area that's been driving a lot of research in this area, because people using the cloud takes too long to get feedback for an autonomous vehicle. One advantage of having on-device algorithms is that you have much shorter latency. There are other advantages as well, which I'll touch on later. But as far as applications where you need immediate feedback and need to make decisions very quickly based on information about your surroundings that you need an autonomous agent to understand, as algorithms get smaller and can run on smaller hardware, it enables things like self-driving cars that can have a small computer in them, or drones, or any sort of other autonomous thing, like something that is these are already out there, things that clean floors, and they go around. Has anyone seen these?
Roombas?
Roomba, exactly, thank you. Are they using deep learning to use some sort of inference visually or probabilistically to...
I'm not sure. I have one in my house.
Yeah.
I don't think so. It doesn't.
I don't think they are either, because I don't think they have a camera built in,
yeah,
or any sort of other sensing. Maybe they have some rudimentary sensing technology.
iRobot does do some rudimentary deep learning.
Really? Okay.
Yes.
Cool.
They learn not only your floor, and they also learn different time, and they're working on one, because iRobot, the CEO is a lady, and they're working on the military version of the iRobot, and it's the same source code, and yeah, they're working on it.
All right.
And they basically have the CPU of a phone. Yes.
Okay. Yeah. So that's a great example that's already in production, already little mini militaries in people's homes, I guess. Is it an actual military application, or is this?
They're building military. They're building security robots.
Interesting. Okay, so this is, yeah, I'm sure that there are, especially in military applications where, you know, like with just drones that are in combat, this is already being used. I personally don't know anything about that. That's a little classified.
If I may say a comment, they're actually looking at, they have a robot that looks like a garbage can that roams around places like Winn-Dixie and Publix, and actually their camera can detect or sense if a person is shoplifting based on by how they act. So the robot will detect whether somebody's doing something suspicious, and all of a sudden turn the 360 camera and phone home and say, hey, you know, looks something suspicious here. So,
yeah.
Again, very simple CPUs because they have to be battery powered.
interesting.
I've heard as well that Amazon, I think with the kind of rumors of iRobot things, they must have some deep learning, machine learning going on. Because what they do is scan your home and they'll look for, okay, this is a sofa, this is a table, oh, they're missing a chair. Can we then send them an email to get this person who owns this, do they want to buy a chair? And so they're thinking on that level of how to use those applications.
Right, yeah, that makes sense too. Anomaly detection for, you should buy this thing to not be anomalous anymore, or something like that. Yeah, so thanks for, by the way, for kind of chipping in. Maybe we can get some other, hey Jack, see you over there. Yeah, so I'm glad that there's some enthusiasm for these ideas here, which is great. It's a little less work for me. Yeah, so also I just kind of wanted to touch on other technologies that have, and where analogous technologies in the past, and where I think today's technology is compared to where other technologies were in the past. So if we think about the transistor, which is hugely transformative as a technology. When it was first discovered, when was it? I think in the late 40s or early 50s. It was a super crappy technology, didn't work very well, but eventually, you know, people made it work a little better, and then transistor radios came about. An interesting story about these I've heard is that the main technology that they eventually replaced, vacuum tube technologies for amplifying a signal. All the manufacturers of vacuum tube technologies, vacuum tubes rather, were not interested at all in transistors because they weren't as good as vacuum tubes for the applications that they were mainly used for. And of course, at first, you know, the transistors then it enabled an application that wasn't possible before, like a pocket radio. And then gradually the technology improved over time, and it kind of took over a whole new market. Similarly, I think with client-side web technology, applications like, I heard that when the founders of Salesforce went to try to get venture funding, venture capitalists would say, well, why should we invest in you? You're making an application that runs in a browser, and browsers aren't very fast. Well, eventually browsers got faster. The whole ecosystem of technologies got faster. Java, you know, or JavaScript and jQuery and broadband became more available. And a similar thing I think is happening with mobile devices. Hardware is improving. The tools in the ecosystem of actually deploying these algorithms to phones is improving. We have every few months, TensorFlow is releasing some new toolkit or sub-library or tool. Same with PyTorch. There are tools for converting neural nets between formats to make them deployable to this type of phone or that type of phone. Different phone manufacturers are there's now CoreML on iOS. I think CoreML has existed for a while, but they're adding new subroutines specifically for deep learning to make common operations like convolutions be more efficiently implemented on that particular hardware architecture. So it's kind of what happened with GPUs, honestly, 10 years ago with CUDA. So before CUDA, people had GPUs, but there wasn't really an easy way to take advantage of them. And then in order for them to become useful, new sets of tools had to be introduced to make it easier for people to make products that took advantage of that technology. And that is happening right now in this space. That's part of the reason why I kind of have a little bit of urgency with this topic, because it's a really special time. I really feel this way. I'm almost getting a little bit of goosebumps, and I get that way with some things. So I'm a little different that way, I know, but I do think that we're, especially with AI that can run on our own hardware, maybe wearables or agricultural devices that can farm for us and not have to rely on large tech companies to do all the compute for us in data centers. I think new types of applications are coming about. Perhaps also similarly with laptops. When laptops were first coming out, you know, these are things that I didn't want to say this. You know, people said that these technologies sucked when they first came out, or they were bad. They weren't fast enough. The batteries didn't last long enough. But things are improving with time. So I think that's kind of where we are right now with this technology. And maybe now would be, I have some demos. I'm wondering when it makes sense for me to kind of go over that. all kind of played out by ear. I'm not going to go into it right now, but okay, yeah. So I want to go over the rest of the talk. How am I on time? Okay. Yeah, mainly I'm going to focus on algorithms. Also, there's hardware and tools. I've already talked a little bit about some implications for what it means for what sort of things can be created in the future. And also there are some, I have some ideas for maybe where, I've seen some recent papers that have been coming out. I have some insight into what researchers are methods and approaches that they're taking to improve these algorithms as well, which is very interesting, as we'll get to later. There we go. Yeah, so, sorry, I don't know why there's this third dot, but most, the history is so brief, and it's still happening that there's a third dot that's not quite done yet. So history's in the making, is what that means. So most progress has occurred relatively recently, and most of the advances in algorithms have been kind of adaptations of taking ideas people have come up for to make larger nets more effective, more accurate, and kind of either just directly downsizing them or kind of trying to understand why they're working so well and kind of move them around in a way such that maybe they can make just like a smaller net architecture work, like punch really high above it, whatever that expression is, like do really well. And so in case anyone here is kind of relatively new to deep learning, I just wanted to give like a brief recap of kind of how we got to where we are today. This is kind of funny. I saw this today. I looked on the archives of the New York Times. They have a hyphen here. This is 2012. This was back when the first big neural net called AlexNet came out. Is anyone here? Who here has heard of AlexNet? Okay, yeah, so it's about like a third of you. So AlexNet was it's named after Alex Kachevsky, who was the lead author on the first convolutional neural network that was successfully trained to really do super well on image recognition. And prior to this, convnets, people had a really hard time getting them to train. Like you could train them, but maybe the network parameters were really unstable, so they wouldn't converge. Or there are a variety of things that weren't working. And what they did then was there were a few recent improvements prior to that algorithmically. And also, one thing that they tried doing, which worked really well, was using GPUs. So a big thing, oh yeah, and also a big aspect was there was a huge amount of data that became available in 2009. And that actually happened in Miami at this like super retro-looking conference. It actually is a very important conference. It happened here in Miami. I'm really happy to hear that. So yeah, this data set called ImageNet, when it came out, it was a database of 1 million images, 1,000 images in 1,000 categories, and it was really important to have this because until recently, it's been like really important to have a lot of data to train neural nets because they have so many parameters. They just need more examples. And so this came out. That really helped a lot with research. And that was unveiled here in Miami, not too far from us. This is when AlexNet came out. This is what the architecture looked like. And basically, you take an image, which maybe has like 3 channels, so red, blue, and green, and you learn kind of spatial patterns in succession. And that's what these are doing, where they're looking at little patches, little local patches of the image. And they kind of detect, in these early layers, I don't want to talk too much about this because I imagine people here are pretty familiar with this, or half of you at least. But in early layers of a neural net, typically it's picking up on things like just normal edges. as you get further layers in, you start inferring things like curvature or circles, more advanced geometric structure. As you get further on from there, you'll learn things like maybe a face, like as a composition of certain geometric structures in a certain spatial configuration. In a way that maybe if you're looking at a painting of Picasso, it wouldn't be recognizable, because in Cubism, as an artistic side note here, you know, it's kind of this spatial reconfiguration of fundamental geometric shapes. But in these, it's learning, certain abstract concepts we can view as compositions of increasingly simple geometric structures. And that's how having these little patches enables you to kind of learn those patterns. And then eventually get into, I'm not going to talk about that anymore. I think we can move on. And then what happened after AlexNet came out is there's a flurry of new big nets. And I say big, because they really were big. This one, it requires, I think, about 2 gigabytes on a GPU, which for a 2-dimensional image classifier is, I think it was the biggest that existed, but it was also the best. And so anyone who wanted to do deep learning basically had to buy GPUs. There was also this here. I'm going to talk a bit about some later nets, because as I alluded to earlier, they were with most of the recent work in small neural nets, they've mainly been adapting innovations in larger ones. And what's happened since this one, around 2014, I think, when it came out, it's mainly now been about being more clever with the types of structures that are in the neural net architecture. Neural nets are not simple anymore. It's really kind of sad. They used to be very simple in this way, like just stacked convolutions on top of each other. Now they're like so complicated, or kind of complicated. If you study them for a while, eventually they kind of make sense. I'm going to try to go through that. So they became more accurate. This is how accurate a neural net was able to classify an image in that ImageNet database. So it started out down here with AlexNet, and 55% accuracy was considered amazing. Now, by the way, phones can do about here at a very fast frame rate, which is pretty amazing. GPUs are very important. They got a lot better over time. It was really good for NVIDIA's stock price. I don't know if anyone knows NVIDIA's stock. This is, as they're kind of getting better here. But also, in addition to GPUs, as I was saying with AlexNet, some really important algorithmic innovations happened around the same time. So, and I say this because I'm trying to kind of move away from, everything's about GPUs, because algorithms are, I think, arguably much more important. Yes, we have the deep learning revolution because of GPUs, but as we know now, we kind of didn't ever need GPUs. If research had continued at its same pace, maybe by now, actually, with the smaller neural nets that are doing really well, we could have kind of been achieving the same accuracy by now anyway, or at least on for the smaller nets. So I don't know how many people here have heard of Dropout? If anyone's like, okay, yeah, cool, yeah. So these things were also very important. Nets were really big. This gives you an idea of how big these these VGG nets were. It's the visual geometry group. They came out with these, and actually now you can kind of see. I wish I could find an image that only kind of had some of the older nets, but in here you can actually see there are some very small nets that relatively small. These are a little bigger. But if you look at MobileNet V2, this came out about 8 months ago. This is a tiny net, and it's doing about 72% accuracy on the not top 5. Like there are different ways of measuring accuracy. This is the strictest way of measuring accuracy, and it's doing better than these behemoths were doing just about less than 5 years ago.
A question.
Yeah.
When you refer to a small net, what are you referring to? The number of
parameters, the memory that it takes up on on a computer, and these devices, or these nets, I think AlexNet was about like something like 20 million parameters. These other ones, they're like less than 2% of it. They're like 40,000 parameters or 50,000 parameters.
So it's the number of parameters.
Number of parameters, but that's a good question, because there are a variety of ways to quantify this. People quantify it in terms of how many images can you classify per second, like how much time does it actually take to classify an image, or how much memory it takes up, how many floating point operations there are that are taking place to run through a net. I think kind of probably the most objective is the floating point operations, or multiply and add, the number of multiply and add operations that occur. I think that's like the only type of operations that happen. And I guess there are also comparisons. Like you have a pooling layer. I guess there's also comparison operations, but multiply add is the metric that I've mainly seen in literature that's talking about like how big nets are, and that is like quite small now.
Is this mainly about like training on facial recognition or something like that?
This is on ImageNet. This yeah, so this is the 1,000 category data set. Yeah, sure. And that has things like different dog breeds,
Right.
a boat,
Right.
yeah,
Planes,
yeah.
drugs.
Yeah, so what happened is accuracy density was pretty low. So accuracy density is a way of kind of quantifying for each additional parameter you add to your model, what's the incremental benefit in terms of accuracy that you get? Like how efficient your model is at being good, in a way. And he's like, I'm really like giving these guys a hard time. The VCG like way up here. And then down here we have these like little nets, these like mobile net v1, mobile net v2, squeeze net, very recent ones. So yeah, we had high accuracy, GPUs were required. Okay, so this is kind of where we get into what actually has been happening recently in the small net space. So since about 2016, there have been, instead of just nets getting bigger, they've kind of been getting smarter. So in the first area here, I'm actually going to go to the next slide. Here, oh, how did the text change? Okay, what? That was unconsented. One aspect is connections between layers. And what these mainly did was they enabled nets to be very deep. Because the issue was if you just had a simple neural net that was really deep, it wouldn't converge. Like once you did back propagation through the layers through a net, and once you got past a certain number of layers, the gradients were just meaningless. The gradients weren't stable. So a way of stabilizing gradients is to add more connections between layers, and that's what DenseNet did. Residual connections as well. Residual connections was more efficient. DenseNet was, as you may infer from the name dense, it literally had a connection from like every layer in the network. But it actually, when it came out, it was the most accurate net that had existed to that time for a little while. And also, there have been these very clever, more complicated layer modules where instead of just having convolutions and max pooling layers being one on top of the other, we have these new types of, or relatively new, ways of capturing the kind of abstractions that I was talking about at the beginning with what's happening at each individual layer. And this is not totally very well understood why these work so well. But basically, what people do think is they're definitely enabling some sort of dimensionality reduction. And I'm not going to go too much into some more like mathematical like framings of this, but it basically enables you to use your parameters to capture a very rich kind of parameterization of different ideas that you have about the world at that level of abstraction. Also, people did did some kind of tweaks with the individual, with simple operators. I'll get into this like depthwise separable convolution. This is actually I don't know, this may sound scary to some people, but I swear it's not. It's just a poorly chosen pretentious name. Also, there's been, this is a very interesting area of research, automated architecture search, where basically net design has kind of been gamified, and with all these advances that have happened in things like AlphaGo or AlphaGo, yeah, AlphaGo is the really famous one, in reinforcement learning, or Atari using reinforcement learning, and also genetic algorithms, which are really neat too. They've kind of, people have been able to test out different net architectures and find what is like absolute best architecture for, and you can also apply a budget of how many parameters you want. You can say, well, keeping my net not any bigger than this number of parameters, what's the best net I could possibly have? And it'll search a space, and I'll touch on that a little later. And there have been other ones too, like these are not the only types of innovations, there have been other things as well, but I don't have all day, so. Residual connections were really clever. So here's this thing here where instead of just having two layers stacked on each other, this is how things were previously with AlexNet or BGG, etc. They have every 2 layers, you actually take the output from one layer and add it as another input to the next set of things, which has this nice way of kind of adding it basically just like stabilizes the data that's flowing through. It makes sure that things don't explode or diminish with the gradients. And that worked really well. And then they were able to have like nets that are like hundreds of layers deep. Also, for some of the larger ResNet architectures, they did these things called bottleneck residual blocks, where, as you can see here, if you have, say, like a layer that has a large number of dimensions, instead of just doing some convolutions on that large dimensional space right away, actually collapse it down to a fewer number of dimensions, then do a convolution, and then re-expand it back out, which is a really clever trick. And this little 1x1, it's called a pointwise convolution, which is a term that I don't like because it's not actually a convolution. It's just taking all of the channels at that individual point and just applying like a matrix multiplication. Just like a mapping from one number of dimensions to another number of dimensions, like in matrix multiplication with linear algebra. And that works really well. And this is also kind of relevant for this like second category of innovations that I mentioned earlier with learning about like reducing dimensionality and having more interesting, more like doing fewer convolutions and convolutions on attributes, like latent attributes that are like more interesting. Or like compressing data within your neural net. And then we're going to see this is going to be used in one really nice architecture that's really small and works quite well. Also, there are these. I'm not going to go into this. It's too complicated, and I need to go faster. Oh yeah, and automated architecture search. I just love this topic of automated search because it sounds so stupid. It's like, okay, all these genius people, they came up with these architectures. Let's just like train a bot to like find the best architectures, and it works. So they just like, they had to do some very kind of special things. You have to, in order to be able to search, you have to kind of like parameterize a search space. It's not that easy to do when you consider how kind of categorical and it's not like you can just parameterize, or how should I say this? The different variety of neural nets you can have, it's like very, you can't just, I don't know how to say it. they came up with this way, though, of searching through a small dimensional space that made the exploration problem more tractable, is what I've read. And they used the kind of exploration approaches that they did were mainly, there are some people who've done reinforcement learning, other people have used genetic approaches, and maybe they would train like 100,000 neural nets and figure out which one was the best. Bayesian optimization is a little different, but that has also been used for things like how do you choose the right learning rate? People use Bayesian optimization to optimize that, for example. That's kind of a related topic. But yeah, so this was kind of the previous state of the art. I think this was about a year ago that all this came out, and then they just like knocked everyone out of the water. And you can also do this here. I think down here they have, oh yeah, multiply and add operations. This is what I was getting at earlier. So if you say restrain yourself to a very small net, they were able to actually find a net that had 74% accuracy with like a very small number of, I don't know what this would be, like 10, I don't know, like about 1,000 billion, so a billion multiply and add operations. So for a gigaflop for going through the, or I don't know exactly how long it takes, but I think it's probably like 100 milliseconds or something. Very fast. So these are kind of a few of the small neural nets that have come out. I will talk about this one next. I'm not going to talk about all these. I'm going to focus actually just on this one and on this one. But there have been some other ones as well. But basically they've borrowed some idea from some big fancy net and kind of transferred it down. And with mobile nets, this was about 2 years ago, less than 2 years ago. You can see here that for a very small model, compared to say, even this one here, from a few years ago, they have a third the number of math you have to do. It's still more accurate. Down here, this is a very small network. This 0.5 is like a factor that they have for adjusting how big this small net is. You have a very small network that actually, so this is about 500 million. This is, if you have just 70 million operations, you can actually have a accuracy that is better than what AlexNet did with like 50 times as many parameters, which is pretty amazing. And this was not even that recent. This was about 20 months ago. And all they did was they just took a normal convolution. They did these things called the depth-wise convolutions. They took a normal convolution, which is typically going to take a certain number of input channels, convolve them spatially, and convert that into another number of output channels. And what they did was they first said, let's actually, instead of doing this big convolutional block, let's just learn one flat convolution for each individual channel. Do that, and then do one of these simple just dimensionality change matrix multiplication things, the pointwise convolutions that we talked about earlier. And that turns out to reduce computation by a lot. If you have a 3x3 convolution, which is the most common size, oftentimes, that means you're doing the 10th of the computation, which is really nice. And you can basically achieve almost the same accuracy. And so this is kind of going over how they're different. So if this is a normal kind of old school convolution, you first do them channel-wise. If they say depth-wise, I like to say channel-wise, because I think just more in terms of like, okay, for this channel, I'm going to do one convolution. It's a very simple, this little matrix patch. And then do that for each channel, and then maybe increase the number of dimensions or shrink after the fact. And this is a way of, in a way, kind of reducing the rank of the convolution that you're doing as well. So it's like introducing this kind of regularization to the convolutions that you're applying at each layer. So it has, because it's less complex, prone to overfitting probably as well. And another more recent innovation, MobileNet v2, developed by a similar team at Google. They basically also did, you can kind of tweak how big it is. They basically show that, well, at any kind of variable size and trade-off that you want to make in terms of how big your model is and how accurate it is and how fast it is, that they're the best. So this was the original MobileNet. The second version has a higher accuracy, it has fewer parameters, fewer operations, and it's faster. And this was actually, it's also better than the reinforcement learned automated search model, which is kind of interesting. So there's still hope for the rest of us. Our jobs are not automated yet. Human beings are still developing better neural nets than the robots are for now. So yeah, it's kind of, again, this is the same error metric that I was talking about at the beginning or some of the earlier slides. This is 75% accuracy, and this was just a little more than a year ago. And there have been, I'm not going to go into some of the other ones, but there have been some even more recently that are even better. And so things are getting better and better on these tiny neural nets, which is really exciting. So I don't know how much, I'm not going to go into the details of this, but just kind of qualitatively, what is happening is a very similar, in a way, kind of a similar thing is with, what it's enabling you to do is, they're doing this here. This is the original residual block, which I think I touched on earlier, where it's, say if you had like a layer with 256 dimensions, you can reduce the dimensionality, then do a convolution in that reduced dimensionality space, and then re-expand later. They actually took that idea and they turned it around, where actually they take a small dimensionality space, they expand it, then they do some very simple convolutions, only depth-wise convolutions. They do the stupid kind of convolution, which is more computationally efficient. And then they get those, and then they collapse it again afterward. And turns out, works really well. And that's how they were able to beat everyone. Where is that? Oh yeah, so these are kind of different sizes, I think, of their model, or size of like image size maybe. And as you can see, the one that the robots made, this NASNet, Neural Architecture Research Net, is up here, and they're like a little better. So they won. And there are others. I'm not going to go into them, but yeah, this ShuffleNet thing, that was more recent. And people basically been, as that kind of slide in the middle that I was talking about, they're either coming up with kind of different modules in neural nets that can reduce dimensionality in some way, or making some of the fundamental operations more computationally efficient. And there are also things that people have done with, I think SqueezeNet maybe did something with like slimming a network, like iteratively removing convolutions or something maybe. I'm not entirely sure. There's like a lot of literature in this space, so I haven't read all of it yet, sorry. And, oh yeah, another kind of related area is object detection. So maybe I'll kind of like give an example. I'm going to stop actually to give an some little demo here. Let's see if I can, okay, here we go. Where did I go? I'm actually going to live cast my phone where I have some small nets that are able to run live. Let's see, where is it? Oh, here we go. Oh wait, that's my Gotta change the input.
Can we identify it?
Here we go. Phone. Does this work? Perfect. So yeah, right here, you can see this is actually MobileNet running on my phone. So you can see it thinks we're maybe in a library, or yeah. It sees a water bottle. It's like, or a bake shop. It's maybe 40% sure. I wonder what it thinks this is. Dumbbell. Okay, it's actually chapstick. But yeah, so this is kind of an example of the kind of accuracy that and speed. You kind of see the latency on the bottom there. It's running pretty fast. This was as of about 1.5 years ago.
Your screen refresh might be hurting it too.
Yeah.
It might actually be doing it faster.
And the I/O streaming video to another device. I'm not sure. But yeah, this is that's that one. And then also you can have a object detector, which can identify chairs and people, and can move and see new things, or here, you guys see the laptop, the bottle. And this is much slower. It's maybe 1 or 2 frames a second, but like we saw earlier, there's kind of a sliding scale. You can choose trade-offs in terms of how fast and accurate you want things to be. So if anyone wants to see more of this later, you can come by.
How much battery it uses? Like,
pardon?
How much battery it uses?
That's a great, horrible question. That's the main thing that's really, yeah, but give me a moment, okay? Oh my God, switch this back.
Are you going to go into how you built the app?
Pardon?
Can you go into how you built the app based on a high level? Did you was that like a did you use Core ML, or what did you wind up using?
Yeah, let me kind of go into that a little bit. So it's there's actually a nice tool you can use to. It was you who was asking me, right?
Yeah.
Yeah. Okay. Sorry. There's this nice utility you can use to, if you've trained a network in say PyTorch or TensorFlow or Caffe, you can convert it to Core ML's compiled type, and then package that in a simple app, and it'll, for most, there are a few exceptions, it'll basically just work out of the box. The main thing where sometimes that doesn't work is if you use a kind of special fundamental operator, like maybe a certain type of pooling layer or pooling operator or something that maybe Core ML doesn't have an implementation for. But basically, yeah, I just, what I did is I didn't even train the model. I just found the model that someone else had, and then I converted it and put it in this Xcode project. I'm not even like I wish I knew more iOS development, because really if you want to like make this in an app, you kind of have to know how to make apps. But for making something simple like the demo, just uses a camera. Does that answer your question? It's because there's not many features in there with the app. So
did you build these demos just for this meetup? I mean, just for today, or?
Yeah, I made it 2 hours ago. I made this like 2 or 3 weeks ago.
That's cool.
Yeah. So,
thanks.
And also, there's a lot of code you can copy on the internet. A few other people are doing this. But a fun thing about this area too is it's not like 100,000 people on the internet are doing the same thing. It's like a few people, which is kind of promising from a, it's like, okay, I'm not like, that you can actually get into this space and be one of the first people working in this space and do something pretty cool. So object detection is like its own separate task. Yes, sir?
For that app, are you using Jolo? For that app, are you using Jolo? You only look once?
Oh, yeah, that was YOLO. YOLO V3. Yeah, I don't know if it's pronounced Jello or Yellow. Yeah, yeah. I recommend, by the way, if you ever want to see the most hilarious academic article you've ever seen, to look up the paper for this. It didn't actually go to a journal, so he just was super humorous throughout the whole thing and ridiculous. But yeah, so YOLO, I'm familiar with how the original YOLO works fairly well. It basically reframes the object detection problem as a regression problem and says that it says, okay, you're gonna have certain boxes of widths and heights and centers, and basically just learns to predict values and just uses normal Euclidean loss to predict values of boxes. And it doesn't. It just goes all through it in one go. It doesn't need any. These other two-stage object detectors, they start with an initial guess, and then they use that initial guess and update the guess with additional information, which actually is more accurate than YOLO, but it can be slower. But actually what these people did here with the light head thing, they actually figured out, they took a look at what was causing some of these multi-stage or two-stage object detectors to be slower than YOLO, because YOLO was the fastest. Figured out how to make the two-stage ones faster, and made this, and that's important because the two-stage ones are more accurate than single-shot ones. But most people seem to there's more written in blogs and stuff about YOLO, but I wonder if that's because YOLO just has a trendy name. I think that may be a big part of it. No one really wants to read about Lighthead, RCNN. Doesn't get as many clicks. But yeah, and the nice thing with these as well is that the most of the architecture for object detection, you can kind of plug and play with different base nets. So if, say, mobile net v3 comes out, you can take someone can train that net on some other data set, and then you just kind of add on a layer or two and things to kind of make the object detection part work, train those bits on your favorite data set, and you're ready to go. So it's a nice kind of extension of all the other work that's happening in image recognition. So to get to what the troll was asking about, batteries. Yeah, so the main cons of doing on-device, any sort of computation, I guess, really not just deep learning. Why is there a rodent on the screen? There we go. Is that obviously accuracy is one issue because you're dealing with smaller hardware, but also battery life gets drained pretty quickly. For the mobile net thing, the first demo that I did where it's just constantly updating, that actually doesn't take up that much compute. Perhaps also because someone was mentioning maybe some of the frame rate time is being consumed by video capture or something that's not necessarily compute related. But the YOLO version that I have here, if I start my battery at 20% and run that app, my phone is dead in like 15 minutes. So you do the math, not that I trust that percentage indicator on my iPhone. You do the math basically means you can run the app for an hour and 15 minutes, and that's then goodbye battery. But batteries are getting better, so I think people tell me they're getting better. And so that's one thing that is a concern, but there are ways around it. But yeah, so also, nice thing with running things on device, as we saw in the demo, it's really fast. You get immediate feedback. You can, if you need feedback within 50 milliseconds, you can, design your net to be even faster. Or if you need things to be more accurate, but you only need an update every second, you can do that as well. Also, one thing that's nice is you're not paying a dime to run any of these algorithms because it's like bring your own compute. Your customers are computing things for you if you're a company running this. It doesn't require internet. Also, data in theory, you can have an app where data never leaves your device, which if your customer is someone who cares about that, maybe it's an enterprise customer who wants to have a really secure application, or a paranoid consumer who doesn't want who really cares about privacy. Not to belittle that, I'm like being a little cheeky with that, but yeah, I mean it's that's certainly not a disadvantage. So perhaps more in general, where that can be useful, yeah, like high throughput applications. Say in general, I think in situations especially where it's like a mechanical situation, maybe where you need immediate feedback. So things, I'm also going to go to the next slide. Like, say you're driving or biking, and maybe you can have your phone set up that it's looking behind you, and it's maybe like speaking things that it sees, or something. Like that could be one application. Or if you're biking, and it's like maybe you can have this thing on the front of your bike, and it detects potholes or something. And yeah, or if like you could use your phone in conjunction with some sort of other mechanical actuator, like a robotics accessory or some other hardware accessory. Also, live music generation, I could imagine being kind of interesting, like something that recognizes what a melody, or not necessarily like recognizing the melody, like, oh, that's this particular song, but something that can recognize the notes that you're singing and like add in percussion or something. Recently, a research group somewhere, I forget what it was, Project Magenta, I don't know who they're a part of, they developed a plugin for Ableton that can automatically generate percussion tracks for any song that you're composing in Ableton. And I can imagine some like very simple version of that perhaps being an app where if you're singing, something automatically can create percussion. And having that low latency is really important there. If you used an infrastructure where it's running in the cloud and then having to wait a second to get a response from somewhere else, that wouldn't work very well. And also potentially, small autonomous entities. Self-driving cars are pretty big, but and where maybe a certain level of accuracy, it requires a very high level of accuracy, but perhaps for certain consumer kind of fun devices, whether it's like a remote-controlled car or a drone or something that maybe you can mount a smartphone with it to kind of be the brains for that device. That could be like a potential application. And did I mention anything else? Oh yeah, so these are just kind of like applications of the pros and cons. So like, well, okay, one con is that it needs battery. So where could it be useful? Where are power sources available? Like in your car, or if you're at work, or if you're asleep, and your phone's charging, or something like that. And I just wanted to wrap up really quick with some kind of ideas of where things could be heading. So in terms of research, I'm not a researcher, but if I were a grad student, I would maybe be wondering like, okay, one thing that's interesting about having a small, simple model is that it'd be useful in ensemble situations. You think about gradient boosting with gradient boosted decision trees. The base classifier is a very simple classifier. Oftentimes stumps are used in gradient boosting. Maybe with neural nets, is it possible to use a very simple base classifier, like a really stupid neural net, but do boosted nets, an ensemble of nets, where each net offsets for errors made by other nets in the ensemble. Or random decision nets as well. Maybe you can have a type of a net that has a really high variance, maybe because certain decision tree models they employ different nodes in the trees only look at certain features. So maybe you could have certain types of neural nets where, extremely random neural nets where each point in like the units in, say, layers of your neural net, you're only considering a random subset of features that are coming, or channels that are coming from the previous layer. That could be something that could be interesting. And where the individual members of the ensemble are not accurate, but where they together are able to be very accurate. I don't know. Perhaps people have already concluded that's a bad idea. I don't know, I'm just throwing it out there. Also, with using architecture research, there's some meta learning happening there. Also, who here has heard of few-shot learning? Few-shot learning, has anyone heard? So with Face ID on your phone, if you think about what Face ID is accomplishing, it's only looking at your face a couple times, and it's able to recognize you thereafter. And it's even able to recognize you in different lighting conditions. If you dye your hair a different color, it's also invariant to age, and how your face may look different at a different age, or with makeup. I mean, they have to be invariant to things like makeup as well. And these sort of things that would vary for the same identity of person. They're able to see past that, and by just looking at a few examples. And that type of problem is called few-shot learning, where you're basically able to classify, learn a good classifier for a specific category just based on a few examples. And this only typically works for problems that are very domain specific. So it works with things like faces. Faces are also a very studied area in machine learning. So we know a lot of work has been done in facial recognition. So it's a domain where we've been accurate. But in terms of small nets, is it possible to potentially train smaller nets from some sort of super intelligent, larger net that is running somewhere else? So that's all I have. I actually have an appendix as well, but I'm not going to go there. Questions? Yeah.
So in one of your slides, you had the different optimizations for MobileNet V1 versus V2 versus, the whole history, right? Like, but with the coming 5G world, like end of this year, next year. In fact, today I just finally noticed on my AT&T, I saw a 5GE. I've never seen that before. So maybe it's like a good coincidence that happened. But like, so what optimizations could be changed with better connectivity to your mobile phone that previously were optimized for low connectivity?
Well, actually, I think 5G enables streaming of video to the cloud more easily. In a way, it means that on-device, perhaps on-device computation is less. There may be some situations where on-device doesn't make as much sense. You would still have to be, the computation would still have to be running somewhere. But one thing I can imagine 5G being useful for even on-device computation, is if you're running a neural net on your phone, actually getting updates from a server about how that neural net should be different based on what you're looking at. Basically downloading new weights, or maybe you're in a new situation and you want to classify something that you don't have a classifier for. Maybe you could download a new model, and it would be a one-time transfer. But with 5G, able to do that? I don't know. Good question.
A question and a comment on that, and then a question. Because we have servers and we use AI for managing servers. And we went to small AI.
How so? What do you mean you use AI to manage servers?
They manage server security, updates, add new users. we have like 8 different small networks that control the servers, one master network that manages them, for lack of a better word. And we have multiple servers, and the reason I'm here, as a matter of fact, is because we don't use GPUs at all. I mean, these are regular, everyday computers.
Yeah.
Right? So we've optimized, but we...
So you could run stuff like this on CPUs on a normal
They're
computer.
running on regular CPUs, and they're small nets, right? So the interesting thing is we have computers, computer grid. We have like 13 or 14 all over the world. And we're using the high-speed network so that the AIs talk to each other.
What do they need? They need to do stuff with security and creating users and stuff.
Yeah, well, for example, let's say somebody tries to hack a server in Sweden.
Oh, okay.
Well, the servers in Miami and Dallas find out about it, and then they get it. Because we read the patterns of what people are doing for hacking, not just what they do, but how they do it, and we establish patterns between them all over the world, right? So this small AIs are actually talking to each other, learning from each other. So that if somebody attacks Sweden from China, or let's say they're pretending to be from France, but they're really from China. Next time they attack Dallas, even though they're pretending to be from Italy, we still know that it's coming from China.
You have to synchronize intelligence, basically.
Exactly. So going back to the phone, the 5G will give the ability for multiple AIs to work as one. And that's something that's actually pretty scary. But think about it. You may be running an AI on your phone, but in reality, we may all be running the same AI. Vis-a-vis Google or whatever, not part client server. So parts running on the cloud, parts running on the. I mean, that's the future. But that's the capability of what's happening with 5G. That's why 5G is such a big thing, because it gives you basically almost unlimited bandwidth, or as much as they want to sell you, on your phone. And yes, you can do a lot with very little AI, with very little CPU power, if you're controlled what you're doing with it. You don't try to do everything.
Yeah, if you are more intelligent with how you use that resource.
Yeah. So my question for you was, when you're running the application, do you know how many CPUs? Because nowadays all these, 2 CPUs, 4 CPUs, how many cores you're actually, is that program running on only 1 core?
No, it's using I didn't say this during the talk. One really cool thing about smartphone CPUs they're not actually CPUs. The GPU and the CPU is the same chip.
Right. So it's running on the GPU on the CPU.
Yeah, it's using all the
Okay.
Yeah, Core ML is definitely taking advantage of everything that it has at its disposal. And I think there's like 500 cores or something on a. I don't know.
It depends on the
don't
phone.
quote me on that.
It depends on the actual CPU, it depends on the model.
Right.
So I was wondering if it was using all of them or just using one of them?
Well, judging from how fast my battery died, I think it's using quite a few.
What's your iPhone model? Because
Oh, I have a bad one. It's from like 3 years ago.
okay, the latest iPhone X's, I think they have like narrow engine.
Yeah.
Which is like more for machine learning stuff, deep learning stuff.
Yeah, and I imagine on an iPad, for example, it would be faster as well. But as far as like how it's using the hardware, I'm not sure. But Apple really, the nice thing with this technology is the wind is at our backs. Apple wants to make this work as well as possible on their hardware, because either Google's going to make something better, or they want to use all the compute available and provide efficient implementations of anything to make these nets run as fast as possible on the device. So,
what are your thoughts on, like, when we're talking about small nets, we're talking mostly mobile right now. What are your thoughts on other devices like AR glasses, like HoloGen and Magic Leap glasses that they were designed with machine learning and capturing the room and having all that technology based on that? Is that being applied right now?
Probably, yeah. Everything that I said about, say, a smartphone. I say a smartphone because it's an example of mobile hardware, basically. Though you could, also, it's basically like non-GPU learning in a way. So yeah, I mean, with these headsets, I don't know what sort of hardware they're endowed with, what sort of processing power they have, but also I don't know how battery life works with them, or
They have a dedicated
same
battery.
considerations.
And
Pardon?
they have a separate battery pack attached.
Okay. Yeah, because I imagine they're doing a lot of other computation too.
Yeah.
So this isn't necessarily a huge additional burden for them.
I've got to play with the Magic Leap headset, and they have to do a room scan, and it's using machine learning. And I was wondering if it's a small net or
Probably. I bet it's an object detector like YOLO or.
Actually, I read about it. They are using NVIDIA Tegra processors for.
Okay, that's the hardware that they're, or the chip that they're using in the headset.
Yeah, NVIDIA Tegra.
Okay.
They have the Magic Leap. You know that?
Yeah.
Magic Leap has a small PC basically with NVIDIA Tegra based PC, which you just have connected to your.
It's like an expandable thing. Like, oh, if you want to have a faster processor, you just like put in this thing.
Yes, it's connected to some kind of processor based on
Interesting.
NVIDIA Tegra.
Yeah.
It works out.
Great. Yeah. That's an area that frankly I don't know much about, but I think there's probably a lot already happening there. Because with object detection, AR is like a very straightforward, useful application. User.
So you mentioned that the deep nets were too large and they got smarter. Is that a trend that's still happening in the industry right now, or is there where we can see a better use of them?
Actually, yeah, I mean, no, people are still making huge nets. I mean, with, who here has heard of GANs? GANs, okay, yeah, so GANs are these amazing, pretty incredible ways of generating examples of images, generating images that look plausible, or look like they could have been taken by a camera in the real world. And in order to do that kind of generation of images, including very high resolution images, you need a really big model. You need to be able to capture very fine detail that exists in images. You need to be able to fool humans that a synthetic image was real, basically. And that takes a lot of compute power. So basically, actually, how I should answer that question is, for generative modeling, big GPUs, or GPUs in general, or lots of compute is required, basically. Unless you're, I mean, if you're doing, I guess you could do some sort of generative modeling that is not trying to be very sophisticated, but for things like GANs, or I don't know if people still use, yeah, I'm not going to go into the other stuff, but yeah. So, yes, sir.
Yeah,
Cedric, right?
That's me. Thank you. Hello, everybody. The app that you designed, have you ever tried to push it any further than you've taken it so far? I mean, did you do any experimentation where you can get a multiple camera setup out of it?
Oh, I hadn't thought about adding in other cameras. But yeah, I think one thing that would be interesting is, I mean, what if you had a drone that had like a bunch of cameras all around, like one of those, what are they called? I don't know, three-dimensional
360
cameras.
view.
Thank you, 360 view, right. You know, do object detection in 360, you know, using your phone's hardware. Yeah, I think something like that would be pretty cool.
One of those amazing things I saw, I was on a bus not too long ago, and a blind person had what looked like an iPhone hanging from a shirt. And the phone said, person in front of you, 3 feet.
Really? Huh.
Pole,
Sorry, was that loud?
curve, yes. And I was going, wow. And I talked to a friend, he says, oh yeah, that's an application, it costs a lot of money, whatever.
Oh.
And they do it from the cloud. But I said, from what you, I'll give you a commercial application of your app. That, you know, people who can't see properly or whatever need to walk around, something like that would do the job perfectly well for them. You know, where you don't need, it's not like driving where you need this super instantaneous response, but it can do, and that, I think that app actually said there was a person in front of you or something like that.
Right.
But you could go further. There's a girl in front of you. you could increase that app so that a blind person can use their phone as their eyes. I mean, the technology's there. It's actually not that far away from that.
Yeah, it's really, yeah, it is amazing how many things are already possible. It's just a matter of what do you want to make. So, yeah.
You mentioned kind of at the beginning that you had an idea for a business, but then you didn't mention what it was. Is that secret, or are you willing to share?
I have, no, it's not secret. I have like a Google Doc of like 50 or 60 things. I need to just like do something simple. What I've actually been like thinking of doing was, I've had like a bunch of ideas, but I don't like talking about ideas because, not because I'm afraid of anyone taking them, but I think a lot of, it's not like, I think a lot of the best ideas at first, they sound kind of silly or stupid, but you know, I think also it's just a matter of like exploring, trying something simple out, putting it out there, see how people use it, and then kind of refining an idea. But like one thing that I've actually, that I would like to make is something similar to, I guess, what perhaps already exists. Maybe I won't make it, but it's something actually that can say, just to using the camera, actually generate sounds that correspond to what it sees. So say like, if you just want to have when you're driving, like point your camera in a different direction or something, and it can just constantly be, you can even have it plugged into your car's system. If you can just have like some additional input, like through one sense, while you're looking at the road with your eyes, what if you could actually get feedback through sound that another observer, namely your phone or an app, is doing that can like inform you about your surroundings. And similarly with like when biking or something. I don't know. The thing is, I think a lot of situations that we think of, they seem kind of not as useful because we have a bias toward thinking of applications that technology already accomplishes. And there's kind of this like chicken and egg problem about like, what is an application that doesn't exist yet that like we don't think of because technology hasn't been able to achieve it for us before. So
watch science fiction movies.
Yeah, science fiction.
They'll tell you what to do.
So I'll take one more question.
So your algorithm, so the algorithm can detect the object in a static way, right? So do you think it's going to be very complicated to add more to compute the dynamic way? That, for instance, you can identify a dog, but you also can identify the dog is running away, or can you add layers to?
I don't know. So I think there are two things that come to mind with that. One is object tracking, which I think actually would be pretty doable, because that kind of reminds me, I haven't done much reading into how, I'm not super familiar with how object tracking works, but I imagine it's kind of similar to how the two-stage object detectors work, where they have an initial guess that flows through with additional current information, then updates the guess, probably with object tracking, of like, okay, there's this dog, then a new frame of the next frame of video comes through, oh, okay, that's still the same dog. I imagine that is doable. But as far as like describing a scene, what comes to mind for that is like scene captioning, which involves like describing qualitatively in words what is happening in a screen or like in an image. That I think is more complicated because it involves it's going from an image to a sequence. At least just thinking in terms of like the particular model that comes to mind for solving that problem. Like you said, could you create something that can describe a situation like, oh, there's a dog running. I don't know if or know about efforts or how complicated it would be or doable it would be to compress some of those scene captioning models into a smaller version. is they use recurrent depths in addition to the convolutions. Have you ever seen some of this work about like automated caption generation for images? It's used by Facebook and Google. Like when you look up a restaurant or something on Google Maps, they have that little caption like trendy bar with, you know, sensibility or something. That's an automatically generated caption based on images that people take into the business. And it's like a certain type of model and everything. But I don't know if that's like quite doable. But thank you so much for your time. I really appreciate it.